Yong-sun, and his title is Model and Evaluation of Impacts of Rooftop PV Panel Installation on Climate and Electricity Supply Demand in Tokyo.
Thank you very much, Professor. My name is Yong Sun, and I'm a PhD student from the University of Tokyo. Today, I'm glad to report our work entitled Modeling and Evaluation of Impacts of Rooftop PV Panel Installation on Urban Climate and Electricity Supply Demand in Tokyo. So I think it's a super suitable report for today's session, focusing on the PV panel on the built environment. So would be the outline. I'll give a brief introduction on the background and the methodology we use to do the simulation, and to discuss the result we got from the simulation result, addressing our research focuses, and finally a small conclusion and discussion. I'll do quickly for background, since we have been listening to these things for these days. The first point is the global increasing uncertainty and extreme weather conditions are observed in recent years and is expected to be more severe in the future. And considering the urban heat island effect, the below bottom figure shows the extreme hot weather happened in Tokyo 30 years before and 30 years later now, and this shows an increasing urban heat island effect in the Tokyo area. So for the second point, because we are measuring and we are considering the PV panel installation and PV panel deployment in urban area, actually both the government and prices in Japan are actually promoting the new technologies and prices for a new transition to the new energy structure. And these are some, sorry, it's in Japanese, but it's some policy from Tokyo government for the obligation for new buildings to have PV panels on their buildings. And the below one shows like distributed PV panel are playing an increasingly important role in the renewable energy sectors. And third part is that actually recently the scientific communities are more and more concerned about the climatic impact from PV panel to the urban system and urban environment. This figure shows the difference between the heat budget model of a rooftop with and without a PV panel. Considering and understanding this background, this study is motivated by, firstly, we recognize the critical role of rooftop PV panels as both an electricity generation system and modifier of urban energy and climate system. And secondly, we think like merely an estimation power generation from PV panel, or we just do some feasibility assessment for this system are currently, I think, not enough to provide satisfactory insights. And lastly, I'm motivated to assess both the energy and climatic impacts of rooftop PV systems under a real situation and do it in a real city, in a real building energy systems. So this study is developed and designed to focus on the following three questions. First is, how does the deployment of rooftop PV panels affect the urban microclimate? This is the climate impact part. The second question is, what is the influence of the rooftop PV panels on the indoor air conditioning demand and the overall building electricity consumption, its impact to the indoor energy demand? And third is, how does an increased PV panel coverage ratio on rooftops would impact the generation and how it could cover the energy demand in buildings? So the methodology we use is CMBM. Thanks to Professor Kanagawa, we could use this model, canopy model and building energy model to simulate the urban microclimate and building energy system in Tokyo. At the same time, so this study, this model is doing a numerical forecast of both urban climate and building energy model by combining the WAF part and the BM part. And the messenger in these slides are two, I think. The first is actually a quite detailed model considering the heat load and heat exchange indoor and outdoor, considering anthropogenic heat indoor and outdoor. The second is, in current our study, especially in Japan, we are classifying the buildings into three types: the detached houses, the apartment, and the office or commercial buildings. So I will introduce the target area in Tokyo. So here we select more than 2,000 force mesh block. A force mesh block is range 500 meters by 500 meters in Tokyo, and you can see the block scale is 2,249. And because we are trying to find out the impact from with and without PV panels, so here we just design three cases. So the base cases means actually we say the different PV panel coverage ratio for different type of buildings in Tokyo. So for the base cases, we have about like 4% for detached houses, apartment is 3.47%, and office 1.6 percentage. And this is actually the real situation in Tokyo. And we designed two actually very ambitious and realistic, sorry, not realistic, idealistic scenarios for called residential scenarios and all scenarios. So residential means all the residential buildings, including apartment and detached houses, are covered with PV panel, and all, yeah, you know what it means. And the simulation period is 1 year. So actually, this scenario setting is quite ambitious and idealistic because it literally covered all the rooftop with PV panel. And one more message is about the rooftop PV panel models. So before actually in CMBM, there's not a very detailed model for the PV panel part because it's mainly calculating the energy in the buildings. But here, we designed two types of PV panel models for the different types of building because, as mentioned, CMBM assumes three types of buildings. And according to the empirical installation evidence in Japan, we designed two rooftop PV panels models to simulate the power generation and heat exchange of PV panel according to the roof type of buildings. And the difference of these two type of models actually just about like whether the rooftop of this building is flat, right? So in Japan, both commercial and office buildings and apartment have a flat rooftop, and for detached houses, they usually have a tilted angle rooftop. And here comes the result. The first, if you remember, the first question we want to address is about the impact on the urban microclimate changes. So here we check the ambient temperature to the average walk because we have 2 9 blocks to show the result directly. We just show the average value. These bars are the average monthly temperature and the WBGT for all the blocks. So there's nothing interesting. But the curves shows the difference between the scenarios, residential scenarios and base scenarios, and the difference between the all scenarios and base scenarios. So we may find actually the deployment of PV panels to rooftop in Tokyo could overall reduce the monthly average ambient temperature and WBGT. But we can find a difference in different months, which we may find the reduction is mostly significant in winter months and comparatively slight in summer. And compared to the base scenarios, all scenarios, ambient temperature will be decreased by about 0.6 degree in December. So we want to know why there's a difference in different months. So we further investigated the temperature changes in the day to check how the temperature is changed in a day for the hourly average temperature in different months. So here we draw the curves for January, April, July, and October. So the conclusion is that, or the findings is, the deployment of PV panel tends to provide a heating effect in daytime and decrease ambient temperature in the evening. And because of the different daytime length and panel temperature in different months, so we may find the PV panel would perform to overall decrease temperature in summer and winter to a different extent. And in July, an averagely 0.163 degree increase is simulated in noon, where the temperature would be reduced a lot, at most about 1 degree in January before the sunrise. So by noticing there's an increasing and heating effect in the noon, we here further checked the difference between a specific period, the temperature and WBGT during 10 a.m. to 2 p.m. in July and August, which is very hot in Tokyo in these days. So we actually find a negative microclimate change is observed in Tokyo when we comparing the scenarios. And we find an average about 0.143 degree ambient temperature increase is observed among the blocks, which means if we have more PV panels, it's actually we're heating when it's hot. And second part is about the electricity demand reduction. So the idea is very simple. Because of the existence of rooftop PV panels, it would shade the heat transfer between indoor and outdoor. Thus, we reduce both the energy demand of AC, both in cooling and warming periods. And this shows the hourly reduction for 2 periods. And averagely, the AC electricity consumption reduction is this value in January and a high value in summer. So we further combine this reduction part with the total energy consumption indoor. And this maps shows the distribution of the reduction ratio for the blocks. And the result is the reduction from AC consumption account for about 5% and 0.5% in total AC energy demand in January and July in warming and cooling period. And to the total is about 0.7% or 1%. And lastly, we are curious about how the supply and demand works. So we first need to calculate and estimate the power generation from PV panels. So these maps show the power generation intensity in each blocks. The power generation intensity for PV panel reaches highest in April, and this falls short in October and January. And actually, there's not a significant difference among the blocks because Tokyo is not that wide range, but we may find actually the intensity is higher at the low-rise part or the residential buildings because it may be led by a shading effect from high-rise buildings in the central area of Tokyo, which means here in the central part, the intensity will be a little bit lower. So we firstly calculate one thing is whether the supply is bigger than demand. So we calculate supply-demand ratio for each blocks. So actually, in the current base scenarios, no blocks could achieve a supply-demand ratio greater than 1. The supply-demand averagely ratio is about like 8%. But when there's for our idealistic scenarios, the ratio is much higher, reaching about like 200%. And in the April, like about 80% and 93% blocks are able to cover the building energy demand with PV power generation. And this is figure about this ratio for the blocks I only showed in all scenarios is quite high level. And yes, let's move to the conclusions. So 3 conclusions addressing 3 research questions. First is rooftop PV panel helps to reduce air conditioning demand, both in cooling and warming periods. And rooftop PV panels reduce overall ambient temperature, but it would potentially accelerate the urban heat risk. And lastly, we found rooftop PV panels potentially provide an excessive power generation in our idealistic scenarios. But for the commercial buildings and office buildings, it still struggles to cover the energy demand in office and these high-rise blocks in Tokyo area. And finally, is discussion. I could stop here. Thank you.
Thank you so much for